In this tutorial, what we're going to do is do a quick CFD simulation of an oblique shockwave over a wedge. The wedge angle will be 15 degrees and a Mach inflow around Mach 2. What we're going to do is first, let me show you, well, let's build the grid and then we'll have a little time while it's running. We're going to be using SU2, Stanford University Unstructured CFD code. It's freeware available, and it's probably its most critical potential is in design. It has sort of built-in control theory based adjoint shape design that allows the solver essentially computes automatically the gradients of your cost function, for example drag with respect to wing shape or shape, and can modify to find the best design within the constraints you give you. It's a pretty incredible piece of software that they've written up in this object-oriented approach, SU2. We'll build a grid with Pointwise, so let me start this. And what we're going to do is just build a very simple mesh. So we'll start with the inflow, and then we'll start to the beginning of the wedge. We'll put it 0, 0. The top of the wedge we'll put it 0.5, 0, and then we'll go all the way back to 6, and then and let's keep making connectors here. Zoom a bit so you can see what's going on. And okay, I think we need one more. It's kind of disappeared. Okay, so let's turn this into a wedge. So essentially we'll have supersonic inflow coming in here. A series of shocks should set up in here. This is a 15-degree wedge, if I did my math correctly. I'm going to do a very simple grid. Ideally we would cluster points near the shockwave, but I don't have time to do that. We don't really need to do that for the simulation. We're just going to use a pretty regular but unstructured grid. I'm going to set the solver here to SU2. So this is a grid generation software, can output different formats. Sadly, there's way too many formats. Why do I not see it? Here it is. Stanford they wrote, okay. And 2D and unstructured. Alright. And now we're going to put dimension, and we'll just make everything about 0.03 units. Okay, and then let's go ahead and create a domain. I haven't used this in a while. I'm trying to remember how to do this. Domain. In a second. Okay, that looks pretty good. I don't think we have to do anything but initialize it. I don't have a sense that this needs to be smoothed. Okay, so like I said, if you were really trying to focus on what was happening over the wedge here, you would put a local grid here, but that requires some clustering and it takes some time. So let's leave this like this. Leave it as it is and define some boundary conditions. So I'm going to put 3 boundary conditions on. Call this how about inlet and outlet and wall. Okay, and now I'll make this the inlet. I'll make this the outlet, and the remaining ones I will make the wall. Okay. Hopefully that'll do. Make sure I have I'll know if the solver is set up properly in a minute. Let's grab this domain. Let's export the model to the directory where I wanted to put it, right here. And we'll call it wedge supersonic SU2. Something there already. That's okay. Okay. Let me try to start this now. See if we can get to run. And essentially what SU2 does is it solves equations of momentum, mass, and energy in each of these control volumes, these little triangular control volumes. You can use a regular grid here. We could have done that. Or a mixed element grid using some quadrilaterals and some triangles. SU2 can handle that, but we're just trying to keep it simple for the moment. So let me get to that directory. And we're there, so let me get that started. I remember the command here. And 8 process will run 8 cores, and the machine will run all 8 cores. And the file name is wedge. We'll have a look at that. That's the parameter file that tells the CFD solver what equations to solve, how long to run, what numerical methods to use, how often to output, those kind of things. And let me hit go, and let's all cross our fingers. Okay, that's a good sign. So it's running, and these numbers that you're seeing or may not be able to see clearly in the video, but essentially these are what we call residuals. They're a measure of the error in solving the momentum and mass equations in these control volumes, and you want these numbers to be as close to 0. That's actually the exponent, so it's e to the -1 and it's crawling towards e to the -2. So let's let it run for a while. I'll go back to my browser. So again, this is the CFD code that we're using. What we're going to be doing, essentially we have a Mach 2 flow, so that's this line right here. This is the oblique shock theta beta Mach diagram. Here's our wedge angle 15. Here's the intersection with, I'm trying to read here, right here, Mach 2 flow. So essentially the wedge angle will be about 45 degrees. We can go to our aerodynamics calculator and we'll see, where are we here? Oblique shock relations, Mach 2, turning angle 15 degrees. It's a weak shock, calculate. Okay, so behind the shock we'll see it's still supersonic, about 1.5 Mach. Pressure jump across the shock is about a factor of 2. Temperature jump about 1.3. And the beta angle, why do I not see it here? Wave angle, which is beta, is 45 degrees. So let's see if the solution has anything to do with that. I'm going to open up my little flow visualizer. Okay, I'm going to open up this file. First thing I'll pull in is pressure. Okay. Alright, so this is the pressure field. I've zoomed in a bit. You can see that the wedge is here. It's a pretty poor solution. Again, the shock is not well resolved, and that's because the mesh is way too coarse for something like this. But you can see its presence there. Let me just go switch this to Mach instead of pressure. Okay. So essentially Mach 2 flow come in. This is our color bar here. Mach 2 flow come in. It jumps to green, which is about 1.5, and that's what we thought it should do, over this wedge. And then over the top of this wedge, consider the diamond airfoils you're looking at. There's a turn. It's a convex turn. So the flow has to turn. It's still supersonic, so it goes through an expansion right here. This is the Prandtl-Meyer fan right here. It's going through. It's accelerating. If we go back to look at pressure in a second, we'll see that the pressure drops across, or jumps across the shock, and then drops across this Prandtl-Meyer fan because there's an acceleration there involving turning this corner supersonically. A key thing is that the shock wave goes up, and something funny happens up here. And what this is called is a Mach reflection. Let me pull in velocity field. I hope I can do that. Give me 1 second. Controls. Hopefully I have to do this without writing the expression for it. I did already. Velocity. Okay, let me add this velocity field. And let's get this to something reasonable to look at. Make everybody the same size. And we'll put it uniformly in the mesh, and we'll put, I don't know, a lot of them. And we'll make them a little smaller. Maybe not that small. Let's just put more of them. Okay, so hopefully you can see this. Let me make it a little bit bigger. Okay, so let me zoom in a little bit here. You can see that the flow, my mouse, give me 1 second, I can make my mouse a little bigger here. Forget how to do this. Damn. I don't remember how to do this. Okay, I don't remember. I thought it was there. Okay, hopefully you can see my mouse on the screen. The vectors come in. See the shock, which is here. You can see how the shock turns the flow. It has to turn the flow because of the wedge. But what happens up here is the flow has been turned by 15 degrees, and now it's coming into the upper wall at an angle of 15 degrees relative to the wall. So something has to turn it back. So you would have another oblique shock wave right here, reflected shock wave, which would turn the flow back to being parallel. So it turns up 15 degrees, now it's going to turn back 15 degrees. So it should be passing through another oblique shock. But because the conditions have changed, we're still supersonic but a lower Mach number, then we have to go back to our oblique shock calculator. And we see here that behind the shock, our Mach's now 1.44 if the flow solution's correct. Still have to turn 15 degrees. I'll change this to 1.44, turning 15 degrees. It comes up with no solution. Why does this come up with no solution? Let's go to the theta beta Mach diagram. Here, 15 degrees, Mach 2, 45 degree turn. That's fine. After the shock, we are at Mach 1.5, and we see to turn 15 degrees, there is no solution for Mach 1.5, which the line would be around here. There's no attached oblique shock solution. So there isn't a solution for an oblique shock that can turn the flow back 15 degrees from this Mach number. So what you get is, and it's not well represented here, is you get what's called a Mach reflection. You can see that there's a big drop in the Mach number here, and you have this region of subsonic flow. This blue region is subsonic flow. You have subsonic flow here. So essentially what's here is a normal shock. And let me show you what you're seeing. It's not well resolved here. This is on the bottom of a tunnel wall, but imagine this upside down. You have the oblique shock coming in from the wedge, wanting to reflect off the wall, but because of the conditions of the theta beta Mach diagram, we don't have an oblique shock angle that can turn it back 15 degrees. So you end up with a normal, just about a normal shock here, behind which the flow is subsonic. So you have a strong shock. The reflection is detached away from the wall. It's a strong shock behind the wall, and then through here you have the turn up and turn back. And so you end up with supersonic flow here, subsonic flow here, and there is a shear layer between them, pretty cool shear layer, which is barely represented here. So you have flow turning up, turning back, but this flow up here is going through a strong shock so that it is subsonic behind. So that's only in these conditions. You can certainly have conditions. If I started with a larger or smaller upstream Mach number, I could have put conditions where, depending on my ramp angle, where I have a regular reflection without a detached oblique shock. But here it's detached. And you can see what happens if I zoom out a little bit. It sets up these series of shocks. Series of shocks going downstream. And that's why it took a while to converge, because the downstream boundary condition I have is not very good for this case. It's tricky, but you can see that the flow comes in, it turns up, it turns down, turns up, and now it's parallel. It's moving through this series of oblique shocks downstream. We can also look at pressure. Let me hide that and add in pressure. And you can see the same thing. You see this big pressure jump across the normal shock, this initial normal shock, which sets up these oblique shock waves. So this might be part of an engine inlet for a ramjet engine, where instead of a normal rotating compressor to compress the fluid, you would use a series of oblique shock waves. You probably wouldn't use a parallel channel like this, but the result is the same. We have a pressure. The pressure is rising, and we have this that other feature I mentioned, which is the Prandtl-Meyer fan. This expansion around this point right here. So that's what I want to say about that. It was just a quick little flow solution. It wasn't meant to be the highest result, but to give you an idea of oblique shocks, what happens in the special can happen in the special case up here of a detached oblique shock and reflections in supersonic flow.